Okay, please excuse the quality of this video also. Again, I'm just trying to get this into your hands as soon as possible. So we're doing note sheet 2, making sure everybody's got the notes. Continuity. A graph is said to be continuous. Continuous. If there are no holes or breaks. This is a pretty intuitive concept. Basically means that the graph never stops. You can draw it all in one big quick stroke without lifting your pencil off the paper. That's really all there is to it. If you can draw it in one quick stroke without lifting your pencil off the paper, then it is continuous. If you need to draw separate branches, pick your pencil up, do something else, then it's not continuous. And not continuous is known as being discontinuous. Pretty simple. If there are breaks or holes in the graph, it's considered to be discontinuous. There are 3 different major types of discontinuity. This one is called infinite. You might guess it's called infinite because it goes off to infinity. I like to think of it as it hits a wall. There are 2 branches to it, and it hits a wall in between, right? Where it goes infinitely off to the top, and it's never going to touch this middle line where at x equals a. So it increases or decreases infinitely as x approaches x equals a from the left or from the right. Just so you know, it's also possible for it to be the same on both sides. So maybe instead of this bottom branch, we have something like this, where it goes up infinitely towards a on both sides, both going infinitely upwards. That would also be an infinite discontinuity. Could also be infinite if it was both going downwards. This one, where it jumps from one place to the other. You're a person, you're walking, and then you have to walk, and then you have to jump to get to the next one, either up or down. That's called a jump. Crazy, I know. This is called a jump. This one, where there's a hole in the graph, guess what? It's called a hole. So this empty circle means everything comes up to here, but right at this point, it starts to just not exist. It just doesn't exist anymore past this, at this one particular point, right there at x equals a. This is also known as a removable discontinuity because you can plug the hole. Plug the hole. A hole or a removable discontinuity. All right. So some examples here. Determine if the function is continuous. If not, identify the type and location of the discontinuity. I'm going to go through these pretty quick because they're very intuitive. All you do is you look at what type of discontinuity it is. So you look, is it going infinitely in both directions? No, it seems to be jumping from one place to the other. So this is a jump discontinuity at, and then you say where it is. This symbol means at, of course. Where is the jump at? Well, you just identify the x value. You can't identify one y value because it seems like, this one x value seems to have 2 y values almost. Now, of course, this one is the true one, and this one is sort of a limiting one. But right here, that x value is where it jumps, where you can divide it into 2 pieces by drawing a line right there. And that is at x equals negative 1, 2, 3, 4, 5. Jump at x equals negative 5. This is the format I want you to write it in. Don't be saying like, hey, this is a jump at y equals, no. The jump is at x equals negative 5. And you can write the word at or whatever you want. This one's continuous. I'm just going to draw the whole thing. And if it's continuous, you don't need to identify where it's continuous because it's continuous everywhere. There's no spot where it jumps from one to the other. Let's go back and look now at number 3. Number 3 here. Okay, so this is going infinitely in both directions. Don't worry about what's going on out here in the end behavior. Look at what's in the middle. See how I can draw that dividing line between the 2 pieces? If you can divide it into this part's over here, that part's over there, and they're totally separate from each other, this is an infinite discontinuity here because it goes infinitely up, infinitely down, and the two branches are separated from each other. And where is it? Well, here's the origin right there. Move over 1, so it's an infinite discontinuity at x equals +1. This one's continuous. Number 4 is continuous because there's no break in the middle. This one's a hole. Where is the hole located at? You might want to be tempted to say the entire coordinates, but don't bother. We're just looking at the x. The hole is at x equals -1, 2, 3. And now number 6 is an example where we can actually have two types of discontinuity in the same graph. It can be discontinuous more than once. So here we go, two different types. Number 6. I see a hole right here, and I see an infinite discontinuity right here. Now they're drawing this line, they're highlighting this to show where it is, where this asymptote or wall is located. But don't be fooled into thinking that that's where the 0 is. 0 is still where it usually is, right in the center, right there. That's the origin 0, 0. So the wall I see, which is called an infinite discontinuity, that's not how you spell infinite. Infinite discontinuity. And where is it located? It's located at x equals 2. 0, 1, 2. And then there's another one, because there's a hole out here. And that hole is at x equals 1, 2, 3, 4. So it's got both an infinite discontinuity and a hole, and they're in two different places. It can have all three types of discontinuity if you want. They just have to all three be in different places. One misconception I see all the time is people thinking that a jump is a hole because they think that, hey, well, there's this open circle right here. Doesn't that indicate a hole? A hole is only if it just is almost continuous. It doesn't do any jumping, but then it's just suddenly at this one particular spot, not doing the thing we'd like it to do. And that would be like this example. This is a hole. This is a jump. Even though it has a picture of a hole in it, it's still a jump, and it's not a hole. Other side, end behavior. So we're talking about how functions behave at their ends. So infinitely to the left and infinitely to the right. So as x moves towards positive and negative infinity, what happens to the graph? We can look at this one. So in this example, as x goes to infinity, f of x approaches, well, I like to imagine this. I am a person standing on this hill. I now walk as far as I can that way. Well, of course, I'm going to have to walk downwards. Am I ever going to stop going downwards? No. I'm just going to keep going on forever. So this is f of x. As x goes to infinity, as we go off to the right, that's positive infinity, f of x approaches negative infinity because we go infinitely downwards as we go off to the right. But what if we go the other way? What if we decide we're going to change direction, go off to the left? Well, maybe I would go down at first, but then I'd start going up again. Up, 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 and we only are worried about what goes on at the end of the graph. What goes on when you go infinitely far in this direction to the left? And, well, it just goes up and up and up forever, and it's never going to stop. So as x approaches negative infinity, x goes to infinity. Now, note on how this is read. As x approaches, or goes to, that's what the arrow means. X approaches infinity, or x goes to infinity. So when x does this, f of x does this other thing. As x does this, y does this. As x does this, y does this other thing. These are two sentences. I like to put a period at the end of mine because they're two separate sentences. This tells you what happens as we go towards positive infinity, go off to the right, and this tells you what happens as we go towards negative infinity, off to the left. In this case, see its opposite, where you go positive infinity in the x, the y goes down to negative infinity. And when you go to negative infinity in the x, the y actually goes up to positive infinity because they're kind of backwards. They say describe the end behavior of each graph. So anytime it says describe the end behavior, all you have to do is write 2 sentences. As x approaches infinity, what happens? Well, put your person on your graph, have them walk this way. It looks like they're going to be stuck around here, going up, 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 up forever, and they're going to go up forever. So f of x goes to infinity. Similarly, on my second sentence, as x goes to negative infinity, see the only difference is that negative infinity telling me I'm going off this way. Well, if I go, I might go down for a second and then go back up and up and up and up and up and up and up, and I'm never stopping. So f of x approaches infinity. Positive because I'm going upwards. Number 8, this side, no matter which way I go, if I start maybe at the peak, you can start wherever you want. If I go off this way or off this way, either way, left or right, my only choice is down. My only choice is downwards, whether I go left or right. So as x approaches infinity, f of x goes down. It goes to negative infinity. It goes as far down as physically possible. And as you go to negative infinity, so you walk this first one was walking off to the right. Negative infinity will be walking off to the left. Well, that also goes to negative infinity. They go the same way. So the difference here, though, I'm going to write this a little differently than I did last time. You may notice we had the same end behavior. Everything was infinity here, except for, of course, it's negative, but both of these were positive infinity on this one. So I'm going to write a shorthand for it, where I'm going to write plus or minus infinity right here. That means as x goes to either positive infinity or negative infinity, f of x goes to negative infinity. Now, of course, you can only do this when the end behavior is the same on both sides. If you had 2 different things here, you can't write 2 things in the same place, and you'd have to write 2 separate sentences. But this plus or minus means the same thing as this, where I just write them as 2 separate sentences. But you don't ever want to put your plus or minus in this part of it, right there, because that's telling you where it's going. Only the last ones can only be either plus or minus, not both. X can be both if it's the same behavior on both sides. Now here we have one with 2 branches. So I always choose the rightmost branch when I'm going off to positive infinity. So I go over here because this is allowing me to go up and to the right. Whereas if I was over on this branch, I could go to the right, but I would not be able to make it past this wall, this asymptote. So if you've got 2 branches or any more than 1 branch, you choose the rightmost branch for the end behavior. Because remember, we're not really worried about what's going on in the middle. All we're worried about is, it's called end behavior. We're worried about what goes on at both ends. So we got our person on the rightmost branch, so they can walk off to positive infinity, and they're just going to go up. So as x approaches infinity, f of x approaches infinity. Then we put ourselves on the leftmost branch so that we can walk over this way. Because again, if we're here, then we're stuck. We can go up and up forever, but we're never going to get past that wall. So we got to be able to go towards negative infinity, go as far left as we want. So if we go off to negative infinity, then it looks like I'm going to decrease, 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 decrease. We're only worried about what happens way off that way, and it goes down. So as x goes to negative infinity, f of x goes to also negative infinity. Now there's one last caveat to this. As x moves towards positive infinity and negative infinity, it doesn't always have to go infinitely in one direction. It could just kind of stop. Here's an example of such a thing. In this graph's end behavior, let's say I am walking here, go off to the right. Remember, this is my right branch for my positive infinity. So as x goes to infinity, f of x goes to, what does it go to? Well, I'm not going up. I'm not going way up. I mean, I'm going down, but I'm going down real slow. I start to level out. Right here. There's the ground. I start to level out at that spot. And I'm not going to get past there. That's my limit. It's no way to get underneath there unless I go off to the other branch. So I'm going walking this way. I'm just going to end up flattening out. It's going to look like this. The graph's going to just stay almost flat forever. It's going to go off infinitely this way, and it's just going to stay flat. The question is, where does it stay flat? And when we say where, of course the x is going to go to positive infinity. But what's the y? What's f of x going to do? Well, it looks to me like this value where the y is would be -1. It gets really, really close to -1. You never quite hit it, but you get so close that it basically doesn't matter. -1. So as x goes to infinity, f of x approaches -1. As we go to negative infinity, similar thing here, but I'm going to be off on this side. Now I'm going to be constantly below my -1 line, but same thing's going to happen. I'm going to get up and up and up and up and up and up and up, and up as I go this way. Up and up and up and up and up and up, but I'm never going to pass this ceiling, that glass ceiling. For those of you into feminism, which should be everyone. So going off to negative infinity, hit your glass ceiling, also at -1. So look at this one, describe the end behavior of each graph. End behavior, so it's the same format. As x goes to infinity or as x goes to negative infinity, what happens? For number 10, I'm looking at as x approaches positive or negative infinity, either one, because it seems to be doing the same thing on both ends. It's not going up on one end and down on the other. On both ends, it appears to be just leveling out at 0. As x goes to either plus or minus infinity, f of x goes to 0. Remember, this is the same thing as writing these two sentences separately. It just lets me do it in less ink or less graphite. Number 11, looking and seeing. I like to see if it's the same on both ends, and in this case, it looks like on one end, going off infinitely, down, 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 and I stop right here. I seem to be stopping at this glass ceiling, glass floor, whatever it is. And on both sides, it appears that I'm approaching the same thing. So as x approaches plus or minus infinity, f of x approaches. Well, what is that value? It looks to be 3 below 0. So that'd be -3. Looking now at number 12, and we're almost done. So looking now at number 12. What have we got? Is it the same on both sides? This way, or walking this way? Either way, we seem to be leveling out right around here. Leveling out, leveling out, leveling out. Is that the same thing over here? Yep. Leveled out at the same spot over here. So, wow, we've got this excellent stroke of luck where we have the same behavior on both ends, both times. So as f of x, as x goes to plus or minus infinity, f of x approaches, what is it getting to? 2. Because remember, this is the y value. We're only concerned with, we know x is going outwards, negative, negative, or positive. We know x is going to be going outwards, away from the origin. The question is, what happens to y? And y seems to be sticking right around this value at +2. It gets real close to it on both sides. Here's one with 3 branches, like what we talked about, number 13. But remember, if there's 3 branches, we don't care about the middle branch, because who cares about what's in the middle? All we care about is what's on the end. So I'm going to choose the rightmost branch, draw my stick figure, going off to the side. He's leveling out right around here. That's where he's stopping. And that appears to be at y equals -2. So as x goes to infinity, f of x goes to -2. Again, because that's where we level out. Same thing on the other side. So I'll just add a plus or minus right there. As x goes to plus or minus infinity. Let's make that neater so that we can actually see it. X goes to plus or minus infinity. F of x goes to -2. If you don't believe me on it being the same on the other side, choose the leftmost branch, walk that way, Looks to be hitting a glass ceiling again. Glass ceiling, you always think you can get past it. Turns out you can't, that's why you gotta break it. This is an infinite discontinuity, by the way, but who cares about what's happening in the middle? All we care about is what's happening at the end. This is here to distract you. Well, it's not really here to distract you, it's just this is how functions look sometimes. But if you're worried about end behavior, I don't care about the middle. You could literally take the middle and just cover it up. All I care about is the ends. At the ends, it looks like both sides, this way or this way, I'm just going off towards leveling out at 0. As f of x goes to, and you can tell my level of tiredness, you don't want to start with as f of x, you want to start with as x. As x goes to plus or minus infinity, f of x approaches 0. All right, and let's finally get one example where they're not completely the same on both sides, which would be here. You can clearly tell that they are not the same on both sides. On one end, if I go off towards negative infinity, I'm just going way up. If I go off towards positive infinity, go towards the right, then I'm leveling off. So I have two different behaviors as x goes to, and it doesn't matter which one you do first. I'm going to do negative infinity first because I'm a rebel here. X goes to negative infinity. F of x goes to, well, if I go towards the left, negative infinity, right, then I'm going up, 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 up. I'm never stopping. F of x goes to infinity. Infinity. Separately, as x goes to positive infinity, what's f of x going to do? Well, I want to see what happens when I cover the whole rest of this graph and just look what's going on right here. Now it's leveling out. Where is it leveling out? At negative 1, 2, 3, 4, 5. So f of x approaches negative 5. All right, those are all the examples. These should be enough to get you through the full practice sheet. Hope this was helpful. Again, give me some feedback on it. I know that the video quality wasn't that good, but I don't know. If you like it, let me know. Otherwise, I'm going to try and make the video quality better. And if you want me to make these shorter, if you want me to make them longer, I don't think you probably want me to make them longer because I talk too long. But whatever you want, let me know so that I can do it.